So selectivity is a measure of how free an analyte signal is from an interference. Interference can be anything that increases or decreases the signal, which is not the analyte itself. If we have something where the measured signal depends just on the analyte and the reagents, then we can simply measure the reagents in the absence of the analyte, do something called a method blank, and then just subtract it. If something's free from interference, so the signal is only due to changes in the analyte concentration, then we can say it's specific. But normally we do have an interferent. Often these are found in the sample matrix itself, in which case the signal that you measure, it's going to be the analyte signal plus the signal for the interference. And it's useful to be able to measure how big an effect that interference has on the analyte. We can do that by using something called the selectivity coefficient, K. So selectivity coefficient for an analyte with a given interference, and the way we measure that is by using small k. Remember, these are the proportionality constants. So signal we know is proportional to concentration, so we use this value k to make them equal, proportionality constant. So k for the interference divided by k for the analyte will give us some measure of how significant the interference is. For example, let's say we have a method for measuring arsenic, and we measure 10 ppb arsenic in the presence of 20 parts per billion of cadmium. And cadmium acts as interference because it increases the signal by 24%. So what's our value of K, our selectivity coefficient? Well, in order to do that, we need to know those proportionality constants, those Ks. This is part per billion. Okay, so we can say that for any signal, it equals a proportionality constant times the concentration. So for arsenic, we can rearrange and say that it's the signal for arsenic divided by the concentration. We know the concentration. The signal we're not given, but we do know it's 24% higher with cadmium. So let's just, it's a relative value, we can just pick a value. So let's pick 100 to make it easy. If the signal is 100 for arsenic by itself, then it must be 24 for cadmium in order to be 24% higher. So it's going to be 100 for the signal for arsenic divided by 10 ppb. And we can do the same thing for our interference for cadmium and say that the signal is going to be 24 and the concentration is 20. And we can put those together for our selectivity coefficient, and it's interferent over analyte. So this is going to be 24 over 20 divided by 100 over 10. And if you do that calculation, we end up with a value of 0.12. And in general, we say that if we multiply this selectivity coefficient by the concentration of the interferent, and it's less than the concentration of the analyte, then it's not a significant interference. So in this case, it would be 0.12 times 20 would give you 2.4, which is less than 10. So this would not be a significant interference.